So this is work about normal form bisimulations by value that some of you have already heard. So this is work with my PhD advisors, Beniamino, Accattoli, and Claudia Faggian. So some of you have already heard about this work, but the new part is the last part, operational game semantics, which I hope I will get to in time. So let's dive into normal form bisimulations, which are a special kind of program equivalence. So I'm interested in studying program equivalence for functional programming languages via the n-type lambda calculus seen as a mathematical models for these programming languages. And the main question I'm trying to answer is, what makes two lambda terms equivalent? So there are various notions of program equivalence, but first there are various notions of lambda calculi. So there are two main paradigms, two main dialects. Call by name, that is the variant that is most used in theoretical studies, that is well known, well understood. And on the other end, we have call by value, which is less studied, but more accurate to actually represent programming languages, functional programming languages. So the main idea behind call by value is that function arguments are evaluated first. So if we go towards programs, programs are usually defined as closed terms. So a closed term is a term with no free variables. And closed terms are usually expressive enough to have some conclusions. You can only study closed terms for many subjects, and they are expressive enough for the modelization of all computable functions or partial recursive functions. But to study certain subjects, you need to really consider open terms, so not only closed terms, but any term. And we'll see that actually in the notion of normal form bisimulations, you need to study open terms. So for call by value, it was formalized by Plotkin, and its theories will behave for closed terms, but not very satisfactory on open terms. And because we'll need to study open terms, we have a problem. So there are propositions in the literature to enhance this open call by value setting to solve this problem. And usually it's the extensions of Plotkin's call by value. So first we have Moggi's work on computational lambda calculus. This was aimed to bridge problems with the CPS translations and also with extensions with effects of the lambda calculus. And we have a more recent attempt towards open call by value, and it's really related to linear logic. And in here, we can have an operational characterization of meaningless and meaningful terms. So what are these meaningless, meaningful terms? There's this thing that in the lambda calculus, not all divergent terms diverge in the same way. Some of them will diverge meaningfully while creating increasing information. That's the case for the fixed point operator. They diverge, but they produce something in every loop. And on the other end, we have really meaningless terms that just loop and create nothing. And this is delta delta. The delta is a duplicator, and when you apply it to yourself, you just are stuck in a loop. And we can say that the meaningless terms are all the terms that are equivalent to delta delta. That's a convoluted definition. We like to have a proper definition of what it is to be meaningful, what it is to be meaningless. And in call by name, that's well understood. That's the whole theory of solvability. So meaningful is solvable, and solvable is also head normalizable. So let's do this in call by value. Let's have a notion of meaningful that is exactly something normalizable. Well, we actually can in Plotkin's call by value. That's the problem. We have this term omega left, which is meaningless because it's equivalent to delta delta, but it's a normal form. Because here, the y applied to y is not a value, so we can't reduce the regex. So that's the problem, one of the problems with open terms in Plotkin's call by value. So we solve it by moving to the open call by value setting. So we actually use the value substitution calculus introduced by Accattoli and Paolini, and it's a conservative refinement of Plotkin's closed call by value, behaves the same way on closed terms, but it does more things on open terms. So you actually use explicit substitution, and if you use these explicit substitution, I don't want to go into detail on how it works, but you actually have the theorem that a term is meaningful if and only if it normalizes with a specific reduction of this calculi. And we have this example of the omega left, where the left regex was stuck, that is solved with explicit substitutions. And you can see that we reach at some point delta delta, and you can see that if we reach some point delta delta, we'll actually loop on ourselves. So now let's go a bit to equivalence of programs. And the most natural one is contextual equivalence. Two terms that behave the same way in this black box principle, that if you feed them entries, feed them inputs, they will give the same outputs. You test this on every input, on every environment, and you test the outputs. So that's very natural. That's exactly what you would think to know whether programs are equivalent, but it's not very usable. That means you have to test on every input. When you have to do a proof, you have to do a proof on every context. It's really hard to actually prove things, and it's like the example that's really hard is the fixed point combinators. You can't really manipulate them and do things. And also that depends on the definition of dialect. Call by name and call by value do not have the same contextual equivalence. So let's go to equivalence of programs that are a bit more general, not only contextual equivalence. And there are 4, not 3, important properties for a relation to be a good candidate to be a program equivalence. Well, it should be an equivalence relation, so reflexive, symmetric, and transitive. It should be compatible, that is, that it's stable under any context, by closure on context. There is this notion of adequacy, that is, if T is in relation with U, then T terminates if only if U terminates. So that depends on the dialect that you use, on the notion of reduction that you use. And the last one is that it should include conversion. So if two terms are convertible, they should be related by the program equivalence. So the nice thing is that if a relation is compatible and adequate, you can directly say that it's included in contextual equivalence. And if an equivalence relation is compatible and includes conversion, then we call this an equational theory. So now we move on to normal form bisimilarity, which is a special kind of program equivalence. So it can be seen as a technique to prove contextual equivalence, but it's very different from contextual equivalence. Remember, contextual equivalence is this principle of black box, you test and everything. Normal form bisimilarity is very syntactic. It states program equivalence for lambda terms by looking at the shape of the normal form. So it really looks at the syntax. For example, in call by value, we relate lambda xt and lambda xt prime by saying, okay, there's a lambda, the shape matches for now, and we look at t and t prime now. So this is really syntactic, and it was also called at the beginning open bisimilarity because we need to deal with open terms. If I move from lambda xt to t, then I'm possibly looking at an open term. So now, usually, normal form bisimilarity is included in contextual equivalence, and the converse is not always true. It's somewhat intuitive to see that it's included in contextual equivalence because similarly written programs will behave the same way in any context. It's intuitive, but the proofs are usually not trivial. And the converse is not really intuitive, and it's often not true. Why would two programs that do the same thing be written in the same way? So normal form bisimulations have been really understood in call by name, like a lot of concepts that have been understood in call by name but are not understood in call by value. So normal form bisimulation have been introduced by Sangiorgi, coming from pi calculus bisimulations, and later refined by Lassen and related with Böhm and Levé-Longotris. They identify meaningless terms because they use the right reduction. They use head reduction. So remember, meaningless is non-head renormalizable. And they are really powerful to me, I guess, because when you add eta equivalence, you get a fully abstract program equivalence. So you actually match contextual equivalence. You're not only included, but contextual equivalence is also included in normal form bisimulations. That's the notion of Nakajima trees. And so these normal form bisimulation in call by name and the trees counterparts have been also studied in relationship with game semantics. I think there's a lot of work on these things. I just stated here, Kerr, Nico, and Ong work on untyped call by name game semantics, which are. So let's go to call by value now that we've seen how it works and we know that it works well in call by name. Why shouldn't it work well in call by value? there's already something that exists in call by value. In the literature done by Lassen, there's call by value normal form bisimilarity that's based on Plotkin's calculus. That's called eager normal form bisimilarity, ENF. And it's not exactly the direct transpose from call by name to call by value, but it's nice. It validates Moggi's laws. The main one I'm interested in is this identity law, that the identity applied to a term is equivalent to a term for all terms. If t was a value, this is really something that is part of call by value. But if t is not a value, this is this classic example. Well, it's not clear that it's not included in Plotkin's call by value, so that's an enhancement of Plotkin. But it differentiates between meaningless terms because it cannot relate a meaningless term, which is a normal form, with a meaningless term, which is not a normal form. So we still have this omega left problem. And this second point is one of the starting point of a work to create a normal form bisimilarity that will identify meaningless terms. So a bit of an overview, because before I go into a little bit more detail, we have 3 bisimilarity that I will present in this talk. There's one that already I've talked about, that is Lassen eager normal form bisimilarity. But we go a bit behind in steps with the naive call by value normal form bisimilarity, which is more natural than Lassen's. And then we go to our main contribution, net bisimilarity. And we'll keep in mind that our goal is relational semantics, which we'll call type equivalence. But I'm going into more detail. What is naive call by value normal form bisimulation? If you just rephrase what happens in call by name, the normal form bisimulation by Sangiorgi, directly to call by value, Plotkin's call by value, you can get an actual bisimulation, an actual bisimilarity that is working. And it's working enough for the main example that is needed for normal form bisimulations. You actually can prove that Curie and Turing's peak point combinators are bisimilar. It's what you can't do in contextual equivalence. And you can do much more. You can't do Moggi's identity law. You can't equate meaningless terms because we're still in Plotkin's call by value. Not a lot of things. That's why we move on to net bisimilarity, and now we can use our setting of the open call by value. So we use the value substitution calculus, as I've told you about before. And because we use this new setting, it will identify all meaningless terms, because by construction, now omega L is not a normal form, it's divergent. And this is called net bisimilarity because we also are able to include linear logic proofnet equivalences. So by proofnet equivalences, I mean that T is in relation with U when their interpretation into proofnets are the same. So one law, I've only written one of the things that are included in proofnet equivalences, is this idea of commutation, that you can actually commute the argument applied to a term. If a term asks for 2 arguments, you can ask for them in one. You can ask for one first or the other first, but you just need to switch the argument. So this is included in proofnet equivalence. I'll call this commutation for the rest of the talk. But it does not subsume Lassen's nth bisimilarity. We still have this problem with the identity law that is not included in Plotkin's call by value, it's not included in the open call by value, it's not included in proofnet's equivalence, so we haven't subsumed this law. So to prove that these normal form bisimilarity actually work, we need to prove that they are included in contextual equivalence, and the crucial point is to prove compatibility. So remember that the relation is tabled under context closures, and we use Lassen's method, which is a simpler Howes method, which was used for call by name normal form bisimulations. So we can prove that nth, well, Lassen already proved that nth was included in contextual equivalence. We can prove that net bisimilarity, the new one we introduced, is included in contextual equivalence. And this exclusion is strict. There is something in the way. Well, there are many things in the way, but the thing I want to talk now is about call by name duplication. duplication. That is inside call by value contextual equivalence. that's a bit weird. I was talking about call by value, now I'm talking about call by name. So because call by value usually does not duplicate, it only duplicates value, but call by value contextual equivalence admits duplication, any kind of duplication. So we're a bit weirded out by this, and we try to find something that is in the middle, that does not validate this weird call by name duplication, but still env and net are included in it. And we found, well, not we didn't found, but we actually see that Ehrhard's call by value relational semantics are in between. So I refer to this as type equivalence because we present them with intersection types, non-idempotent intersection types. So we have this situation now that we have these two bisimilarity, which have an intersection. The intersection is not empty, but they are really orthogonal. And there's not one that is bigger than the other. We have, on one hand, the identity law, on the other hand, meaninglessness, and the proofnet equivalences. But let's zoom in a bit on this type equivalence, because I haven't shown you anything that maybe their union actually matches type equivalence. That's not, so we can prove that it's included in type equivalence, and that's actually easier than proving that it's included in contextual equivalence, easier than proving compatibility. But this inclusion is, again, strict. There is a problem with eta v equivalence. So eta v is just a reconstruction on values of eta equivalence. And so this inclusion is, again, strict, but it's less of a problem if we want to reach type equivalence, because eta is not a problem for env bisimilarity. It's been really studied by Lassen and then improved later on in other works. But it's still a problem for net. If we wanted to add eta to net, we would need to add the identity law, Moggi's identity law to net, and we don't know how to do that. But the conjecture is that type equivalence is exactly env, net, and eta. We haven't have any examples of things that aren't in one of these categories, let's say. So now I can talk a bit about operational game semantics. So where does the game semantics fit in this picture that I've shown you now? So this is a bit of a guess, because there are no untyped call by value game semantics, so I can't really say where it is, and I haven't done any proofs. But they are untyped call by value operational game semantics, so maybe that can help as well. Just a few ideas on why I put the game semantics there. Game semantics validates Moggi's identity law usually, so it should include Moggi's law. Game semantics do not usually validate commutation, so it shouldn't really include all net. And I think any respectable model should identify meaningless terms. I think that's a thing that any model should do. And games, I don't think they usually validate duplication of resources. I think that's not something that any first games that you draw will do. But this is really guesses and less well followed than, there are no proofs on here, whereas the first part of the talk was more worked on. And the bit operational game semantics, I think they are a more structured version than a more structured normal form-based simulations. There's a lot of connections, and I think people usually use the term interchangeably. I'm surprised that they use a different method for compatibility. I've never seen Lassen's or Howe's method used to operation game semantics. And so env and operational game semantic, Lassen's bisimilarity has been really studied in OGS, improved. I think next talk is about, the base of next talk is Lassen's bisimilarity. But we do not know what's the relationship with operational game semantics and net bisimilarity, the new bisimulation we've introduced. So to conclude, we've investigated and related 3 call-by-value normal form bisimulations and 1 denotational equivalence, so the naive call-by-value Lassen's bisimulation, net bisimulation, and type equivalence. Maybe what's missing from this list is game semantics, because we've not followed everything. We've not done an actual work to relate all with this with game semantics. But the main thing I want you to get out of this talk is that call by value situation is richer than call by name, and when call by name contextual occurrence can be basically just summed up as head normal form by simulations up to eta. If we want to do the same thing in call by value, so the translation of head normal form is naive call by value normal form by simulation, we need to do up to eta, up to identifying meaningless, the identity law, proof net equivalence, duplication, and whatever else we haven't found yet. We can push some of these inside, that's the purpose of net by simulations, but we still haven't the full picture, and we still don't have full abstraction. Thank you for your attention. This is the final picture.
So there is time for one question. Yes?
Thanks. Maybe it's a comment rather than a question, but anyway, you said at some point no game semantics for untyped call by value. But I don't think I would really agree with that, because Guy McCusker made game semantics for call by value with recursive types. And once you have recursive types, you can form a type D, you can define the type D, which is D arrow D, and that would be sort of a version of untyped call by value sitting inside call by value with recursive types. It may not be the version of call by value that you want, but that would probably maybe be similar to the one that Lassen did in that 2006 work. So that would be a denotational work.
Okay, so I'd have to follow up on that, but the thing is whether game semantics are actually build on the types, or maybe you can give game semantics in this framework for untyped, but to build the framework you need the types.
Oh, you mean you would like to see it presented just for an untyped?
Maybe.
Okay. Right, thanks.
Okay. Let's thank Adrienne again.